looked at single and double replacement reactions in detail, we're going to look at one last type of reaction, and that is a combustion reaction. So a combustion reaction is a reaction between a hydrocarbon, which in this first example is C2H2, and that hydrocarbon is going to react with oxygen. And what is produced every single time is carbon dioxide and water. Okay? The important other thing that is released is heat or energy. And that's why when you think of a combustion reaction, you often think about some sort of explosion. But that's all there is to combustion reaction. So really the most challenging part of a combustion reaction is balancing. So let's work on that right now. So for this problem, C2H2, I'm going to first balance my carbons. I've got 2 on my reactant side, so I'm going to put a 2 in front of CO2. I've got 2 hydrogens on my reactant side. I've already got 2 on my product side. So let's figure out how many oxygens I now have. I've got 2 times 2, so I've got 4 from carbon dioxide, and I've got 1 from water, so that's a total of 5. Well, how in the world can I get 5 oxygens on my reactant side? What times 2 gives me 5? Well, 5 halves. Okay. Now, no, I cannot, or 2.5. You can do 5 halves or 2.5. Either one is fine. It doesn't matter because, first of all, they're the same number, but also because you can't leave a coefficient as a fraction. So instead, what I'm going to have to do is multiply all of my coefficients by one single number to get rid of that fraction. And so the reason why I write this as a fraction, it's pretty obvious now that to get rid of the over 2 part of this, I need to multiply everything by 2. So there's an implied 1 in front of C2H2, so I'm going to multiply that by 2, so that'll just become 2. 5 halves becomes just 5. CO2, that becomes a 4 in front, and since there's a 1 in front of water, that becomes a 2, and I am balanced. Okay, let's work on the next one. C4H10, it combusts. So I'm giving you C4H10. Okay. It is going to react with oxygen to produce carbon dioxide and water again. Okay. So I have 4 carbons on my reactant side, so I need to put a 4 in front of carbon dioxide. I've got 10 hydrogens on my reactant side, so I need to put a 5 in front of water, because 5 times 2 is 10. So now, if I count, I've got 8 oxygens from carbon dioxide, 5 from water, which gives me a total of 13. So I need to put 13 over 2 in front of O2, because that'll give me 13 on my reactant side. So just like the previous problem, I now need to get rid of this 13 over 2, so I'm going to multiply everything by 2. So there's a 1 in front of C4H10, so that'll become a 2. 13 over 2 simply becomes 13. 4 becomes 8. And 5 becomes 10. Okay, let's work on one last problem. C2H5OH, this is a hydrocarbon. This is alcohol. Alcohols are very flammable because they will perform a combustion reaction. So the issue and the reason why, just a quick side note, this reaction will not occur unless you have a spark. That's why it's so dangerous to smoke or to have any sort of flame near a gas station. Same thing with alcohol. Alcohol burns readily as soon as you provide it with the energy needed for the reaction to start. We call that the activation energy. So if you have alcohol out, yes, there's oxygen in the air. It's not going to spontaneously combust, but as soon as you provide some sort of a flame, it will produce a lot of heat. So you've got to be careful. Okay, so I've got 2 carbons on my reactant side, so I'm going to put a 2 in front of carbon dioxide. Now be careful because I've got a total of 6 hydrogens on my reactant side, so I'm going to put a 3 in front here. And so what that gives me for oxygen, I've got 4 oxygens from carbon dioxide, I've got 3 from water, so that gives me 7. Do be careful because I already have 1 oxygen here from my alcohol. So what that tells me is that I only need to have 6 oxygens from O2 to give me a total of 7 that I want on my reactant side. So all I have to do is put a 3 in front of oxygen here, and I am now balanced.